Hello everyone, and welcome to my session on using CXL with AI applications. My name's Steve Scargall. I'm a Senior Product Manager at MemVerge. And you've heard a lot from our hardware partners as part of this Memory Fabric forum talking about the lower level hardware and how that all works. I want to bring this up a level and kind of describe a little bit more about what we're doing from the software side. And obviously AI is very prevalent these days, so I wanted to describe what we're doing, at least some of the work we're doing with regards to AI, and specifically for this talk, I want to focus on the database side, so vector databases and SQL databases. So this is the agenda I put together for my session. I'll recap the memory expansion form factors, what they are, the two different factors, and how they fit into your server. I want to talk a little bit about the latency and bandwidth memory placement strategies. So these are the policies that we've implemented in our own MemVerge memory machine that allow us to utilize the hardware that's available to us dependent on the application requirements. And then I'll show you some of the investigations that we've done. We've taken a deep dive into traditional RDBMS databases, so MySQL, and vector databases. In this example, it'll be Weaviate. Show you the results that we're getting from our memory placement strategy policies. And then I'll talk at the end about how you can better understand your own application behavior, and I'll show you some of the tools and approaches that we take in this area. So here we're kind of represented a standard 2U server, 2-socket, either Intel or AMD, it doesn't really matter. The DDR modules plug into the DDR slots, again, either 1 DIMM per channel or 2 DIMM per channel, dependent on the number of slots available to you and your requirements there. As far as the CXL is concerned, there are two predominant form factors. There's the add-in card that looks like a PCIe slot. It has the PCIe Chem form factor. And again, dependent on the vendor and the capabilities and features of that card, you can plug in your own DDR into here. So the flexibility of these devices is that you can define the capacity based on the number of DIMM slots that are available to you and the capacity of the DDR modules that you put in here. We expect that many of the vendors will support either DDR4 or DDR5. So if you're moving up to the newer servers that have DDR5, you can recycle your old DDR4 and plop them into these add-in cards. Alternatively, if you want the highest bandwidth, go and purchase the DDR5 modules with these types of devices. Another advantage here is that because they are a Chem factor, predominantly they fit into a by 16 slot, so you get maximum bandwidth out of these devices. The other form factor is the E3.S. So it kind of looks like an NVMe drive, and you intended to put these into the front of the servers, as we're showing here, very much like you would install front-loading SSDs. The disadvantage here is that they're typically only by 8, so you've lost half the bandwidth necessarily from the add-in cards, but you can usually fit more of them into the system, so you can regain a lot of the bandwidth if you're able to fully populate a system here. The capacities are fixed, of course, because you can't install your own media into an E3.S, so at least the ones that have been advertised by different vendors typically are in the 128, 256, and 512 gig ranges. So again, depending on the capacity and the number of slots available to you, you're able to expand the memory of the server with this. Now, I don't know if we're down to the OEMs, but I haven't seen anybody that allows you to do a mix of the two, right? So you're either going to be E3.S platform or you're going to be an add-in card-based platform. And that's really because if you go through the E3.S route, you're moving a lot of the PCIe lanes to the front of the server. So the PCIe slots available at the back are typically going to be for, I don't know, maybe a GPU or a network card or two, right, to allow you to connect to your external networks and storage. So we do not expect to see servers supporting both add-in cards and E3.S memory modules. So now we've described the hardware side of it. Again, I want to bring it over to the software side. So how do these hardware devices, these CXL memory devices, get exposed? Well, there are many different ways of doing it. I'm just going to describe one, and that is that in the BIOS, we configure the CXL to be what we call special purpose memory. And that means that the BIOS maps the memory in to the EIT20 table, and it passes it through to the Linux kernel, and the Linux kernel understands that this is now a software reserved memory area. So you get this contiguous chunk of memory, depending on how many devices you have. Now in that mode, the kernel will automatically create what we call a dev DAX or a device DAX namespace type, and you'll get this entry in /dev called DAX x.y. Typically starts at 0.0 and goes up from there, depending on, again, on how many devices you have. And that's just a regular character device, right? So if your application wants to just memory map files, you can memory map this device into your application address space and treat it as regular memory, doing load store operations, right? But the application itself, it then becomes the memory allocator. And whilst it is the best place to be doing this type of intelligent memory placement, it does require that the applications be modified. Now, if you don't want to modify your applications, we can convert this device DAX into a regular NUMA node that we call system RAM in kernel terms. And you just run this command that I'm showing on the screen here. So the DAXCTL reconfig device, change its mode from dev DAX to system RAM, pointed at the device that you want. And then that memory appears to the operating system as a new NUMA node, but it does not list any CPUs. So for example, in the example we're showing here, node 0 and node 1 are our two sockets on the server. They have locally attached DRAM, so that's the 64 gig that you're seeing here, plus the number of CPU cores. And then node 2 is our CXL device, so it just comes up as 128 gig of available memory, and that again is a NUMA node, right? So applications that are NUMA aware could potentially use this without modification. However, you can use tools such as NUMA control and other things, C groups, to ensure that your application can use both DRAM and CXL without modification. So we've just described how the memory gets mapped into the operating system and made available to the applications, but then how does the application really use that, right? So I'll first talk about the latency placement policy. And the intent here is that now we have this system with heterogeneous memory, DRAM being the lowest latency memory tier, probably fairly high capacity, maybe up to 1 terabyte or 2. In addition to the CXL that's available to you, again, dependent on the number of devices and the capacity of those devices, you should have fairly high capacity of that as well. But the CXL will have slightly higher latency, right? So you don't want to treat these two things as equal, because they're not. But what you want to be able to do is take advantage of the fact that you now have CXL in the system. So the intent around latency tiering is that we identify the hot pages or the hot memory. Those are the pages that are touched most frequently. And if DRAM becomes full or near full, you want to be able to use the capacity of CXL. So we want to identify the cold or cooler pages, those pages that are not touched as frequently, and move those to CXL. Now the application is still going to be able to access them in CXL. It's still a load store operation, so nothing really changes there. It's just that it has slightly higher latency. But it's still better than going to disk, right? The alternative to this is that you would have to page memory in and out of disk, or even worse, have to go to your swap device, right? So this definitely has a significant advantage for applications. So our memory placement policy does this. It does it transparently to the application. So the applications continue running, and in the background we're monitoring the temperature of the pages and moving them to the appropriate tier. So we can do what we call demotion, so moving data from DRAM into the next level of memory tier, which is CXL, and promotion, which is then if that cold page becomes hot, you would ideally want to move that back into DRAM and maybe move some data in DRAM that's now cooler back into CXL. So you're able to move this data around. Now the kernel itself also has a similar feature. It's called transparent page placement, TPP, and the feature was upstreamed by predominantly Meta. It initially got upstreamed into the 5.16 kernel with demotion only, meaning that it could only move data from DRAM to CXL. But in the 5.18 kernel and onwards, it can also do promotion. So now again, it's doing similar things to us, where we can move data between the tiers dependent on the frequency of how often those pages are accessed. So here are the kind of results that we got when comparing our own MemVerge memory machine latency policy with default kernel TPP policy. As you can see, ours is the blue lines. We normalize these charts relative to the TPP results. So the transactions per second higher is better, of course. We do, for the most part, a much better job as we increase the number of clients along the x-axis and the transactions per second as a percentage on the y-axis. Relative to that, we've got queries per second, so we're able to do more queries per second as the number of clients increase than what we would call the ambient or the TPP implementation. Because of that, we're able to reduce the latency of each query by about 20 to 40%. That's the lower left chart here. And on the right hand side, you can see that we actually use a little less CPU in doing this work as well, again, relative to TPP. The bit towards the beginning of the chart that shows a much higher result or lower result, depending which way you're looking at this, we think that's mostly CPU cache related. So these newer CPUs from Intel and AMD have significantly higher L1, L2, and L3 caches. So the lower the number of clients available, that's a CPU caching artifact there. So the second memory placement policy that I want to talk about is bandwidth, and this is very similar to interleaving your DRAM or striping across drives for a RAID set, for example. Right, we're trying to maximize and utilize all of the available bandwidth to us from all of the devices. Now, again, depending on how many DRAM modules you have in the system and how many CXL devices you have in the system, or whether they're using by 4, by 8, by 16 lanes, will determine the characteristics and bandwidth of the CXL device. So what we want to be able to do is utilize the strategies of weighted interleaving, that meaning that we probably want heavier weight on DRAM and not as much weight on CXL when we choose to move pages around. Similarly, we can also look at, say, random page selection. So if we know what that ratio of DRAM to CXL bandwidth is, we can just take a random selection of pages from an application or many applications and decide to move, that ratio down to CXL. The one that we're now looking at is intelligent page selection. So this is using heuristics of memory pages and not necessarily making an immediate decision, but using some historical amount of information to decide which pages or page ranges should be moved to DRAM or CXL. Now, unlike the latency, we do actually end up with hot and cold data on DRAM and CXL, because again, this is a bandwidth play, not a latency play. But using either streams or Intel MLC, you can determine the actual bandwidth and throughput of your DRAM and CXL devices. So that helps us to calculate this ratio that we need to understand what weight we should place on CXL and DRAM for our algorithms. So I wanted to kind of show you an example, right, using a bit of napkin math here. We can use, again, either streams or MLC to determine the real bandwidth throughput of our DRAM and CXL devices. So the example I'm providing here is that we use our lab system that we used previously for the results, which had 8 DDR5 4800 DIMMs installed, 1 DIMM per channel for maximum bandwidth. That gave us an approximate 300 gigabytes per second. Now, if we install an add-in card that uses by 16 lanes, that gave us an approximation of 60 gigabytes per second. So the ratio between DRAM and CXL in this particular case is a 5-to-1 or a 20%, right? So that gives you a rough starting point for determining what ratios you should be using with the bandwidth policy. So using our bandwidth policy in the memory machine, these are the results we got from Weaviate. Weaviate itself is a vector database, pretty popular out there in the AI world. We use the standard benchmarks that benchmark tool, I should say, that Weaviate provides us with. Now, the benchmark tool itself has, I think, 4 different major tests. I think there's a SIFT, there's GLOVE, Deep Image, and GIST. Each one is designed to test the database with different sizes, so different number of objects, and a different level of number of dimensions in the vectors. GIST 960, which I pulled out here, has 1 million objects and a depth of 960 dimensions. So that's the GIST 960 Euclidean here. And here I'm showing the number of queries per second that we were able to achieve with bandwidth. And this is using both DRAM plus CXL. You can see that we normalized the results to just DRAM only. So here we took the same system, we ran the benchmark in DRAM only, and then we did DRAM plus CXL with our bandwidth policy. So this is the uplift that we got by using just a single CXL device. The charts here, the 6 bars, the first 3 bars represent the 90-10 ratio. So 90% of the data lived in DRAM, 10% lived in CXL. And then the 3 bars, the benchmarks limit, or have this for the variable called limit, that limits the number of results that you get back per query. So the first bar is limit of 1 result, then it's 10 results, then it's 100 results. So you can see here that at least with the 10 and 100, the orange bar and the dark green bar, we're getting a little over 7% here. The last 3 bars, the blue, the purple, and the green, when we did a split of 80-20. So if you remember from the example, 80-20 was the actual theoretical limit of bandwidth for DRAM and CXL. So the best optimal solutions fit somewhere between 90-10 and 80-20. Although, having said that, we continue to refine our software and improve performance, so we would expect these numbers to get better in the upcoming releases. And then this is the same benchmark, same hardware, same test. This is just the P95 latency. So again, we are positive is better in this situation. So again, with the maximum kind of returning 100 queries for 100 vectors per query, we're very close to 9% better in terms of latency, which was reflected in the previous chart where we're able to do more queries per second, right? And then, let's get on to kind of understanding your application. And this is where we can kind of get down into the weeds a bit, right? The CPUs are very complicated these days, many cores, many ALUs, and a whole bunch of other, very intricate things that go on inside of the CPU to make sure that the CPU can handle the workload that you're giving it, right? So these 2 diagrams are really just kind of, one shows a representation of a CPU, what happens inside of it, and we call it front end and back end. And then the right hand side is kind of a decision tree as to, okay, how do I get from running my application to understanding if this is a speculation problem, is the CPU just speculating, going and getting the wrong data or getting data that I'm never using? Or is it what we call front end and back end? So is it more compute bound or is it more memory bound? And I'll put a link at the bottom of this slide here, so you can kind of go read a little bit more on this if you want to. But this gets down pretty deep into understanding what's happening inside of your memory controllers, your CPUs, and other subsystems. So the other tool that we commonly use is an open source tool from Intel called TopLev. Works better on their CPUs, obviously. By using this example, we're using our stream benchmark under TopLev, and it shows that we are memory bound. So in the center here, it says backend underbar bound.memory bound, right? And it's 20% in here. So we're spending quite a bit of time memory bound, which is what we expect for stream. It's a very complicated benchmark, and it's doing a lot of vector lookup. So we do expect it to be memory bound in this situation. But again, you can run this against your application and see for yourself, is this more memory bound or compute bound, etc. So just to give you an idea of another tool that's available. So finally, here's a list of resources that you can go learn a bit more, engage with myself and other industry partners and experts. So, first there's the website, the memoryfabricforum.com. You'll find a lot of resources on there. Our YouTube and SlideShare, where you'll find the recordings of this webinar plus the slides, and previous sessions and future sessions as well. We have a LinkedIn group, so you're welcome to go learn more there. And then finally, for more real-time updates or asking questions, there's a Discord link there. So that's the invite to go and join our Discord server. A couple of different rooms in there. You're welcome to come ask questions or learn more. We're usually posting information around events like this as well. So this is more of a real-time event. So I appreciate your time. Thank you so very much. I hope you have a good rest of your day, and we'll catch you on the next one.